Welcome to Bite-Sized Data Science. Let's continue where we left off in video 60. I am using the IBM Watson Studio environment to run my notebook. If you are interested, you can find a link in the description on how to create a free account on that platform. Links to the notebook I'm using here are also available in the description. In video 60, we identified categorical fields and created reference tables for their categories. We can see here that we have a list of categorical columns in the cat columns variable. I also created another variable, other_cal_columns, to list the categorical columns that already have numerical values. For context, I reused some code from video 60 to display the values distribution for all categorical columns. Like I said in video 60, some modeling works better with less choices in a categorical field. Let's do a quick review, taking the speed limit as example. The speed limit includes 31 different values. We can see that we have suspicious speed limits. To reduce the number of categories, we could either remove the records that have a suspicious speed limit, or we could group them in 5 mph increment. This is something to discuss with the business owner of the data. Since most accidents occur in 30 mph zones, I believe we could simply ignore the speed limit or divide it in two categories, 30 mph or not. At this point, we analyzed our categorical fields and made the decisions listed here. Used 3 groups for traffic control device, used 3 groups for device condition, used 2 groups for weather condition, and so on. In video 60, we created all the categorical tables. We now need to modify them to reflect the grouping, and we need to add tables for the categorical fields that were already numerical. Our first step is to modify all the reference tables we created and add an additional column to each of them. The alter table statement string used 2 arguments. Argument 0 represents the schema name, and the argument 1 the column name. The reference table names are simply the column names followed by _table. We can then alter the tables by simply looking at the column names. Note that the default value for the grouping column is 0, which will serve as the default group for a category. The second step is to create the reference tables for the numerical categorical columns listed in the other_cat_columns variable. The table definition is very similar to the previous ones. To populate these tables, I have to use a slightly more complex SQL statement since both the ID column and the description column must be set to the same value. It is still pretty simple. Now that we have all our reference tables, we have to update the grouping columns in each table to reflect the decisions we made earlier. There is no easy way to do it, but we can still use Python to make it simpler. We defined 2 update table statements templates. One to update specific grouping values, and one where we do no grouping, so the grouping column must be set to the ID value. Let's take traffic control device as an example. We have 15 categories and we only want 3. Since grouping defaults to 0, it then represents the other category. We only need to change the grouping value for category 12 and 13 to be up to date. The Python code simply loops over the target categories and set their grouping to increasing sequential values. In our example here, we set the grouping to category 12 to 1 and category 13 to 2. All the other categories stay at 0. For categorical attributes like report_type, we are not doing any grouping, so we set the grouping value to the ID value. This is needed for consistency for later. There is one more thing I want to mention in terms of data understanding. Correlation. We can look at the numerical columns in our original table to see if there is correlation between them. If 2 columns are highly correlated, one of them can be removed from our modeling since it does not add any additional information. To do this, I could read all the data into a pandas data frame and then use the core method to get the correlation. Instead, I take advantage of the IBM DB-py package to do the same thing from within the database server. This ends up being more efficient since I don't have to move all the data to my notebook before doing the correlation work. We can look at the result as a table, but here is the result as a graph where light colors represent a high correlation and dark colors represents inverse correlation. Anything in between shows lower correlation down to no correlation at all. The obvious insight of this graph is that injuries_unknown is useless for modeling. We're ready to create the final Chicago accident table. Once again, I use Python to help create the SQL statement. I first retrieve some basic information on the columns from the database server catalog. The second step is to loop over the column names and change the definition if they are our target columns. In that case, the column name is replaced with the same name with the _ID added to it, and we add a reference to the related table we created earlier. Once the table is created, we can populate it, again using Python to help in the SQL statement creation. There is a lot more exploration that can be done to better understand the data. At the same time, we can restructure the dataset to be more efficient, as we saw with the data normalization. Hopefully, this short video on data understanding and preparation gives you an idea on why data science projects spend most of their time in this area. See you next time on Bite-Sized Data Science, and don't forget to subscribe.